I think I can give you voice.
Great. Thanks a lot for the introduction, and it's my great pleasure to present our latest work on the adversarial vulnerabilities of large language models. So yeah, so maybe a quick introduction about myself. So I'm currently a fourth year computer science PhD student at UIUC. I'm also a research assistant advised by Professor Boley at the Secure Learning Lab. And in the meantime, I'm also a part-time intern at NVIDIA Research. And previously, I had multiple like research opportunities at Google Research, Microsoft Research, and Alibaba Group. So my research focus mainly lies in like trustworthy natural language processing, and specifically it includes the following three sub areas, including robustness, privacy, and ethics of language models. So in today's talk, I will mainly focus on the robustness side of uh, trustworthy NLP models. So, um, so in today's talk, we will cover essentially two papers, and the first paper is SemAttack, natural textual tags for different semantic spaces. So this paper is just accepted to NAACL 2022, and it's about how to design a like general framework to conduct textual adversarial attacks to examine the vulnerabilities of large language models. And this is kind of gives an example of how to design an adversarial textual attacks, and then we'll move on to with this like designed like text different kind of text attacks, how to give a comprehensive and principled analysis of how robust my language models is using our proposed adversarial GLUE dataset. So yeah, maybe let me get started. So yeah, let's first talk about the SemAttack one. So to have a little bit of background of what adversarial attacks are. Um, uh, so recently we find that deep learning networks can be broken with some carefully constructed adversarial examples. So, for example, an image classifier initially classifies the benign panda image correctly, but when some adversarial noise is injected in the picture that is like totally imperceptible to human being, the resulting prediction of the adversarial example is changed to another animal like gibbon, even with a much higher confidence. Um, and adversarial examples exist in not only in image domain, but also in text domain. So for example, the last figure shows you an adversarial example for QA system that adds an like distracting sentence to the QA model and make the QA model output the wrong answer. And the right figure shows you an adversarial example for classification models that performs adversarial word substitution to replace words to their synonyms and achieve the attack goal. While in our work, we want to propose a generalized attack framework. And specifically, we want to answer the following two questions. So first is during like textual attacks, for example, for a classification model, how can we perform legit word substitution to make sure the semantic meaning is not changed? So this is the also aligns with our first contribution that we propose adversarial token substitution on this kind of constraint on different semantic spaces to retain like the semantic meaning, and it's also generalizable to other languages where we experiment with both English and Chinese. Um, and the second question is, how can we find which words to replace to achieve the attack goal For example, like this, why we finally consider to replace characters, we replace this contrived instead of this characters. And this aligns with our second contribution on how to design a efficient optimization objectives such that we can minimize our perturbation while achieving the attack. And in our work, we focus on essentially two attack goals. The first attack goal is called untargeted attack, meaning that our attack is successful as long as we like make the model's output to predict a wrong answer that is different from the ground truth class. And another setting is called targeted attack, which is a much stronger attack than untargeted attack. Our attack is successful only if we make the model's prediction to be like aligned with our like predefined target. So, for example, given the image classification model, if our target is cat, then we want model to output whatever images to output cat as the targeted class. So to achieve the previous mentioned two goals, our first contribution is we propose the semantic perturbation functions to constrain the like adversarial substitution to like within a certain spaces, and this is achieved by some general form and which is called semantic perturbation function f. And essentially, this function takes a token x and tries to map this token x to a semantic perturbation candidate s. So we assume those like tokens in this semantic perturbation candidates are all valid tokens, and are all valid tokens for adversarial substitution. And we design different semantic perturbation functions, which can be defined on different like semantic spaces for different languages. So as an example of how we can design these semantic perturbation functions, we consider the following three perturbation spaces. But we know that we can definitely design our own like rules for semantic spaces to make sure this like adversarial word substitution or perturbation is sense making to human being. We and specifically we consider typo space that like map a token to a token x to its like typo while still sense making to human being, and also map a text under the guidance of some knowledge like WordNet. And finally, we use some like existing BERT models to construct a contextualized semantic space to map this token x to semantic meanings to tokens with like close semantic meanings. And we focus on the following two languages, English and Chinese. And we find this the proposed three spaces all can be applied to these two languages. Yeah, so specifically for typo-based perturbation space, we try to constrain the search space as in the typo space. And for English, we essentially for each token x, we construct the search space as by inspired by the recent work called TextBugger. And essentially, we follow the following 5 principles to construct a typo. And essentially, for example, we can insert a space into a word or delete a random character of a word and swap a random two adjacent letters in the word to like mimic the typing arrows and replace the characters with the visually similar characters. For example, replacing O with digit 0. And lastly, replace the characters with adjacent characters in the keyboard, again, to mimic the typo arrows. And an example is, for example, for word token word, we in the typo-based perturbation function ft will map this word to W0 RD or WO space RD to mimic this typo space. And for Chinese language, we consider the following two transformations. For example, for each token X, we will find Chinese characters that look similar or have the similar pronunciation or opinion. So, for example, given this token May, we will try to which means beauty. We'll try to use this typo-based perturbation function of t to map it to a very similar Chinese character, or some Chinese character share the same pronunciation. Yeah. And the next example we consider to construct this semantic perturbation function is called knowledge-based perturbation function (FK). So essentially, we constrain the search space as while some existing knowledge bases, and here we use the existing rule-based knowledge base called WordNet. So this is a large lexical data set and contain synonyms more than 200 languages. And for both English and Chinese, we just use WordNet. And for each token, we just query this synonym as from WordNet. But note that we do some additional filtering, we want to exclude hypernyms and hypernyms and include some synonyms with low frequency of part of speech property. And an example is for token clean, we will use this knowledge-based perturbation function fk to map it to a token blank or token unaffected. And lastly, we propose a novel contextualized semantic perturbation function fc. So the main motivation is that so we want to have a search for contextualized perturbation while BERT embedding space to tackle the polysemous issues of natural language processing. And we also hope that our proposed methods can be adapted to other languages with just a pre-trained language model. So given these two motivations, we try to construct our search space by the following steps. So first of all, we will select a commonly used tokens X, like around 10K or 20K of common use tokens. And then for each token X, we'll select 100 examples from Wikipedia to set as a demonstration of different meanings of X in different contexts. And then we'll obtain the contextualized embedding for each word X. So finally, we will have 100 contextual embeddings for each word X. And we will put all of these tokens, embeddings of each tokens together, summing of search space, which is like this. And during query time, we will for each token X, we will query this large BERT embedding space using k-nearest neighbor, and to choose the closest high-frequent semantic neighbors as the search space X. An example is for the query query token experienced, which serves as a verb in this sentence. We'll use this embedding of experience in query in this BERT embedding cluster. And we find that the close neighbor of experience are all about experience, witness, saw, seen, had, that is related to the verb meaning of this experience. And given a experience as an adjective context, we input this like adjective experienced embeddings and query this BERT embedding clusters, and we find that the close neighbors are about like expertise, skilled, good, and things like that. And then we'll return those closest high-frequency semantic neighbors as the search space as. So with this, like previously mentioned, 3 perturbation space, we can construct a valid perturbation set, and which can answer our question of how we can like find legit and valid word substitutions to retain the semantic meaning of the previous sentence. And now we can answer our second question on how we can efficiently find which words to replace and finally achieve our attack goals. So specifically, we answer this this question by formulating the problem as a 2-phase optimization problem. So in phase 1, we will optimize the perturbation. So now the perturbation is first injected on the word embedding space, and we will minimize the perturbation such that the perturbation norm is minimal while achieve the attack goal GX. So we formulate the attack goal GX to the following loss function. So for the target attack scenario, the GX is we want to our target logit as large as possible, and even larger than confidence threshold kappa. And in the untargeted attack scenario, we want to whatever large target, as long as it's different from the ground truth, then our attack is successful. And we also hope the final like wrong logit is above some threshold kappa. And with these 2 attack attack goals and their loss functions, we can using like gradient descent to find the minimal perturbation E star. Well, note that now the E star is still in the like word embedding space. So in phase 2, we'll perform real token substitution to find the tokens that mostly close to this perturbation E star. So specifically, we want to constrain this word substitution process to be constrained by our previously proposed semantic perturbation functions called FT, FK, and FC. Yeah, that's essentially the main protocol of SemAttack. And in our experiments, we conduct comprehensive experiments to different language models and different tasks. And specifically, we our experiment setup is as follows. So in the attack scenarios, we will focus on 2 settings. The first setting is some kind of ideal setting to give a proof of concept experiment to show our method is indeed work and has high effectiveness. And this scenario is called white box attack, meaning that we have the full access to the model parameters, and thus we will have also the access to models like gradient information. So this makes everything quite easy to optimize. While in some cases, or in most cases, the model parameters or even output will not be available to you. So to mimic the worst case, like attack scenario, we consider the scenario called zero query black box attack, meaning that we have no access to the model parameters, we have no idea what the model is like, and we are unable to query the model's outputs. So in this scenario, we can only use like transferability-based attack to attack the model. and essentially we'll examine the transferability of our proposed method. And in this scenario, we'll use some surrogate model, for example, BERT or Roberta, that is trained by ourselves, and generate adversarial examples against it, and use this generated adversarial examples to attack those black box models. And in the attack task, we follow the following two tasks, which are sentiment analysis using Yelp dataset, natural language inference using SNLI task. And in terms of attack capabilities, we consider both targeted attack and untargeted attack. And the targeted attack is evaluated by targeted attack success rate, meaning that how many samples are successfully achieved targeted attack divided by all samples. And we consider for sentiment analysis, we consider the most strongest attack, meaning that we want to flip the Yelp reviews prediction from like the original less than 3 stars, the negative review, to the exactly 5-star, the most positive review. And similarly for Yelp review with large than 3 stars, that is positive review, we want to attack it to 1 star, which corresponds to the most negative review. And in an NLI setting, we map the contradiction neutral to entailment and entailment to contradiction to set our target goal. And for untargeted attack, we evaluate our untargeted attack success rate by untargeted attack success rates, which is essentially the number of samples that achieve untargeted attack goals divided by the number of total samples. So so in our white box attack setting, first of all, we attack some BERT and self-attention LSTM to demonstrate that our proposed attack can be applied to both state-of-the-art language models, but also like LSTM models. And we focus on tasks like sentiment analysis, which is shown left, and natural language inference task, which is shown right. And we compare with other like white box attack method like hot flip, and we find that our proposed method can successfully attack like a BERT model or self-attention LSTM model from their previous accuracy of like 0.7 to almost 0%, as we achieve like almost 97% of attack success rates, with only like around 4% of the sample of the words are perturbed. And similarly for the SNLI task. And here we also want to give you an adversarial example of what we finally generated. For example, in the sentiment analysis task, we just flipped the word trip to voyage and successfully make the model prediction from 1 star to 5 star, which is most positive review. And for the SNLI task, similarly, we just flip one token from by flip this token hit to smashed, and successfully make this a model prediction from contradiction to entailment. Yeah. And secondly, we focus on the more realistic attack scenario called zero query black box attack, and we've now focused on some state-of-the-art language models and some defense methods on the NLI task. And specifically, we focus on the BERT large, and FreeLB. And we find that compared with other like black box attack methods, our SemAttack still achieves the highest attack success rates, and with like smallest perturbation rates. And moreover, we find that in this transferability-based attack, the title-based attack somehow has the best transferability compared to all other methods, which can be as high as like 90%, for untargeted attack. We also know that for targeted attack scenario, in the transferability setting, it is much less effective than targeted attack. And then in our experiments, we try to adapt the SemAttack to Chinese and to attack Chinese BERT. And we find to demonstrate the generalization of our method. And we find that our method still achieves the state-of-the-art performance than existing baseline and can make the model's output to as low as 99% with a few like perturbations. And lastly, we will make sure the quality of our generated adversarial text is valid and makes sense. So we conduct another round of human evaluation. And this human evaluation will focus on two orthogonal metrics. The first is called language quality, and this is conducted by asking human how like fluent and sense-making this sentence is to you from a scale of 1 to 5. And in terms of the utility, and we also evaluate the quality of adversarial text in terms of preserving, meaning that after we perform adversarial attack, how many labels are preserved from the human perspective. And then to evaluate that, we just send the sentences to humans and let them to label the sentence and say what's the performance gap between the clean samples and adversarial samples. So we can have a quick look at the results. So in terms of language quality, we find that in the Yelp data set, we just do a few samples of perturbation, which is the smallest among all baselines, and with also like very small perplexity and BERT score. And then in the human ratings, we also have very similar performance with the state-of-the-art method like BERT attack. And similarly for the Chinese data set as well. And in terms of the utility preserving, we find that the performance gap between the clean data set and our generated adversarial data set is very close, meaning that our human will barely be affected by our generated adversarial examples, while BERT models can, like the prediction accuracy can drop to 0. Yep. That so far is the content of our proposed SemAttack. So now we can move on to Adversarial GLUE dataset, which is a multitask benchmark for robustness evaluation of language models. So remember, note that we in our previous setting we just introduced an attack method as an example, and now we can also like take the aforementioned attack as some like evaluation toolkit. So essentially, this toolkit performs some ad hoc input perturbation to test model robustness. But the problem is that as we just perform in past experiments, we need to conduct like a lot of human evaluation to guarantee the quality of the transformations. While to give a like a comprehensive robustness evaluation, we must like employ like very strict human annotation to make sure our generated attacks are of high quality to both human and machine learning models. And from another perspective, the existing benchmark datasets are either using some handcrafted templates or rules to construct some challenging test cases, or just to let the human to be this attack algorithm, or just to let human to write adversarial examples and attack machine learning models. So the problem is obvious that this data set has very limited scalability and comprehensiveness. So to solve the aforementioned problems, the goal of our adversarial GLUE benchmark is to try to have a comprehensive understanding of model robustness by set up a unified and principled robustness evaluation benchmark for natural language models. And we also want to answer the following two questions. So from the perspective of adversarial attacks, which adversarial attacks is most effective, transferable, and stealthy to human, and how likely can human be fooled by different adversarial attacks? And from the perspective of large language models, we want to answer the questions of what types of language models are more robust and what kind of adversarial attacks the language models are still vulnerable to. So first, we want to briefly introduce our procedure to build this unified and principled robustness evaluation benchmark. So to give an overview of adversarial GLUE, our dataset consists of the following 5 representative and challenging tasks in GLUE, which include sentiment analysis using SST2, duplicate question detection using QQP, and natural language inference, including MNLI, RTE, and QNLI. And our evaluation protocol is actually the same as the mean that will follow the same train data and evaluation metrics. And the reason we designed this is because we want to make sure the model developers can clearly understand the performance gap between the models tested and this ideally benign environment versus the models that is in approximately worst case adversarial scenarios with our adversarial GLUE dataset with just one-time training. And the taxonomy of our adversarial GLUE consists of the following sections. The first section is word level attack, where actually we just introduce our SemAttack to give an overview what existing word level attack looks like, and we also include sentence level attack and human level attack. Let me have a quick introduction of each word level attack means. So specifically for our adversarial GLUE dataset consists of the following 5 representative word level perturbations. And these types focus on either typo-based attack or embedding based attack or contextualized attack, knowledge-based attack, and the composition of the following 4 types. And this is implemented by the text bugger, text fooler, BERT attack, SemIMI PSO, and SemAttack that we just introduced before. And the explanation is actually very similar to the framework we just introduced. That is, in the first step, we using some optimization techniques to identify important words, and then we'll replace those words with their specific strategies. For example, given the typo-based attack, text bugger will replace huge to HUGE with a space inside. And for the embedding based attack, they will replace the words with words sharing the close cosine similarity of embeddings, such as replacing chest to torso. And the contextualized attack, the BERT attack will replace the important words by pre-trained mask language modeling and which is similar to mask these words and perform mask language model prediction to replace it with some candidate words. For example, replace cold with sleep. And in a knowledge-based attack implemented by SemIMI PSO, while using some external knowledge base such as HowNet or WordNet, and replace words like influenced to infected. And in the composition of the following attack we just introduced, we use SemAttack and replace them with the composition of the previous strategies. And for example, replace bubble to this bibble. Since we have just introduced this, word level perturbations, I guess you are quite familiar with this setting. And then we can move on to sentence level perturbations. For the sentence level perturbation, it can be roughly divided into two categories, which is called syntactic-based perturbation and distraction-based perturbation. So syntactic-based perturbation tries to perturb the sentence to paraphrase the sentence or manipulate the syntactic structures of the sentence, while distraction-based sentence will insert some unrelated sentence to distract the model attention. And specifically for syntactic-based perturbations, we use SCPN for syntax tree transformation, T3 for context vector transformation, and ADV fever as rule-based entailment-preserving transformations. And for distraction-based perturbation, we follow the strategy proposed by stress test and checklist to add some meaningless sentences to the end of the sentence to distract model's attention, such as "and true is true" or some website links. And lastly, we will cover the human-crafted examples. And this can incorporate some template-generated datasets such as stress test and checklist, and as well as some existing adversarial datasets like ANLI and AdvGLUE that employ human annotators to generate adversarial examples. So that finally, our adversarial glue can cover more like linguistic phenomenon and have a comprehensive understanding of model robustness. After we introduce how we generate our raw adversarial examples, we then need to do some careful and additional rounds of filtering to ensure the quality and the validity of our generated adversarial examples are sense-making. And specifically, we consider the following two types of filtering, which are automatic filtering and human evaluation. So specifically for automatic filtering, we'll evaluate the generated adversarial examples along two fronts, which are transferability and fidelity. So transferability will evaluate whether the adversarial examples generated against the one source model can successfully transfer and attack the other two surrogate models. And in our paper, we consider BERT, Roberta, and Roberta Ensemble as the source surrogate models. And only adversarial examples can successfully attack those three surrogate models will be kept to ensure the examples have high transferability across models. And then we perform another round of filtering to ensure the generated adversarial examples maintain the original semantics. And for word level perturbations, we ensure the word modification rate is less than 50%. And for sentence level perturbations, we will only keep the adversarial examples with the highest BERT score and discard the rest of the sentence level generated adversarial examples. And in terms of the second round of filtering, we use human evaluation to verify the quality of the generated adversarial examples. And first of all, since glue task is a little bit difficult for human annotators, and we make sure human annotators can fully understand the glue task. So each worker is required to pass the training step to be qualified to join the main filtering phase. And in the main filtering phase, we will first filter examples with high consensus and only keep examples with at least 4 vote consensus. And we also ensure the majority vote labels is the same as the original label to ensure the attack is valid and utility preserving. And after all of these steps, we can finalizing our dataset, and specifically we'll merge our curated dataset for word level perturbations and sentence level perturbations, and merge them with human crafted examples, and forming a very high quality benchmark consisting of around 5K high quality adversarial examples. And the full data generation pipeline is shown here. So after we collect our collect and finalize our robust evaluation benchmark dataset, we can now answer our previously raised question, that is from the perspective of adversarial examples. Which adversarial attack algorithms against language models are more effective, transferable, or stealthy to human? To answer this question, first of all, we will need to introduce the following evaluation metrics to measure the effectiveness of adversarial attacks. Since we have introduced SemAttack, I guess you are very familiar with attack success rate, ASR. And then we are interested in the curated attack success rate, or called curated ASR, meaning that among all the filtered adversarial examples, how many of them can still successfully attack the downstream task and models? And here's our main results on the evaluation of attack success rate and curated attack success rate. So we can see that while most attacks show high attack success rate, the curated ASR is always less than 11%. So this means that most existing adversarial attack algorithms are still not effective enough to generate high-quality adversarial examples that can survive in our previously strict filtering protocol. And among all attacks, we find that TextBugger and T3 achieves the highest curated ASR in the word-level attacks and sentence-level attacks. So this also aligns with our previous finding in SemAttack that typo-based attack somehow actually has the best transferability among the baselines. And then we want to ask how likely the human can be fooled by different adversarial examples. So this is measured by the evaluation matrix called validity, and specifically consists of the following three metrics. The first is filter rate, that measures how many examples are rejected in the data curation procedures and reflects the noisiness of the generated adversarial examples. And we also use Fleece kappa to measure the annotator's agreement rate on collected data, and also human accuracy to estimate the human performance on the collected data set. So the evaluation results is shown here. So let's first have a look at the filter rate. So in terms of filter rate, we find that adversarial attacks, like the filter rate is more than 85% for most adversarial attack methods. So this suggests that even existing strong adversarial attack methods are still prone to generating invalid and nonsense adversarial examples that either change the original semantic meanings or generate ambiguous perturbations that hindered annotators like understanding. And we also note that the Fleece kappa before filtering is quite low, meaning that the adversarial examples might have like wrong labels and confuse the annotators quite a lot. And after the human annotation and filtering, we find that the curated Fleece kappa increases quite a lot, to around 0.6, which is aligns with some existing high quality data sets like SNLI and ANLI. And after we look at all of our existing adversarial attacks, we can now have a look at existing state-of-the-art large language models. And we can first answer the question, what type of language models are more robust? So we can see that, first of all, we find that although state-of-the-art language models have achieved a high performance on GLUE dataset, they are still vulnerable to various adversarial attacks. For instance, the performance gap can be as large as 55% on the smart BERT in terms of the average score. And in terms of the all tested models, we find that the BERT and ALBERT achieves the highest AdvGLUE scores. And this is also aligns with the leaderboard on the ANLI. And we also note that although our adversarial examples note that it's generated from BERT and RoBERT, but after data filtering, our generated adversarial examples still have very high transferability between models after curation and successfully attack electoral models that we have never seen before, as well as the T5 and the BERT. And lastly, we evaluate some like defense strategies such as SMART, FreeLB, and EFOBERT. And we find that the RoBERT improves the RoBERT Smart improves the RoBERT Large over 3.7% accuracy on average, and it actually even slightly improves the binary accuracy as well. And lastly, we can have overview of what kinds of adversarial attacks these large language models are still vulnerable to. So here we will give a diagnostic report of the models we examine. And we find that actually among all of these existing attacks methods, the human-crafted examples are, first of all, highest quality and also achieve the highest attack success rates. And we find that those models are most vulnerable to these human-crafted examples. And we guess the reasons is because these adversarial examples can cover some very complicated linguistics phenomenon, including like a numeric reasoning, negation, and coreference resolution. And in terms of the sentence level perturbations, we find that models are more vulnerable to distraction-based attack than directly manipulating the syntactic structures. And in terms of the word level perturbations, we find that models are similarly vulnerable to different word replacement strategies. And among all of them, the typo-based and knowledge-based perturbations are most effective attacks. So finally, to give some conclusions, we present Adversarial GLUE, a multitask benchmark to evaluate the robustness of language models. And we find that most existing adversarial attack algorithms are prone to generating invalid or ambiguous adversarial examples. And from the perspective of large language models, we find that existing state-of-the-art language still perform poorly on AdvGLUE, with scores lagging far behind the benign accuracy. So we hope our work can inspire the development of like more stealthy and more semantic preserving adversarial text for language models. And on the other hand, we hope our work can also motivate the more like robust models that is like capable to defend against those complicated adversarial attacks and have a more robust accuracy in the worst case of adversarial scenarios. All right, that's pretty much the presentation of today. Just let me know if you have any questions.
Thank you very much for your presentation. I actually think it's a very important topic, as like in computer vision, everyone knows about adversarial examples. And in NLP, I'm not sure if many people are aware of that problem and in making the models safe. And I wanted to ask if you have tested some popular models like GPT-3 or something with your data set?
Yeah, actually, we have tested the GPT-3 dataset using our AdvGLUE benchmark. And I think we include those results in our appendix. The reason we do not include it in the paper is because actually GPT-3 is an autoregressive generation model. It's actually not that good at doing like downstream tasks like the GLUE dataset. So they typically has low test accuracy on those GLUE benchmark. And of course, under our adversarial attacks, their accuracy even drops further. Yeah.
Yeah, okay. I've got the other question. Like, do you have the pipeline to create like that data set with adversarial examples? Like, you can give you the data set and the pipeline will give you the adversarial data set?
So you mean the pipeline like this?
Yeah.
So yeah,
like the automatic one, not the human one.
Yeah, so for the automatic one, we for some because our benchmark consists of like a large range of existing attack algorithms, and most of them are have open source their code. We just use it and run to generate adversarial examples. And for the human annotation one. So we have actually have and open sourced our human annotation protocol in our adversarial GLUE leaderboard. So specifically on how we train our humans and that human to filtering given our like design instructions.
Yeah, that's great. I don't know if anyone has other questions. Okay, if not, then thank you very much. It was a very nice talk. And I hope that the awareness of people of this problem will grow. And yeah, I think it's very important.
Yeah, the robustness of large language models are indeed a less like explored domain, I would say, compared to like the popularity in the computer vision domain, but it's actually a quite important problem. And I hope our work can motivate the development of more robust language models to appear. Yeah, thanks a lot for the invitation. And
yeah, and thank you a lot for your work.
Yeah, just let me know if you have further questions. We can also talk offline. Thank you.
Thank you.
Bye-bye.
Bye.